For this lab, we're going to take a look at calculating the mass of a black hole utilizing data that was supplied from a CVS spreadsheet. A black hole is an enormous star, 10 times more massive than the Sun, that has been compacted into an approximate size of the diameter of New York City. The result of this compacting produces a gravitational field so strong that nothing, not even light, can escape. One problem with investigating black holes is the 1,600 light-year distance between the Earth and the black hole. This image is an artistic rendering of what is believed a black hole may look like. Not having a black hole to demonstrate with, I decided to start the lab with a demonstration showing how a black hole may be thought of on Earth. This demonstration shows the non-zero force and the increasing period of the ball. As the ball rolls around the funnel, the ball's parallel force, called momentum, keeps it from immediately dropping through the hole. Some of the gravitational potential energy is converted into kinetic energy. This results in a higher velocity as the ball nears the black hole. To begin, I started to construct a Python model. First, I edited the scene display as indicated on the screen. I found that it was best to modify the display height and width and turn off the auto scale option. I also modified the size of the star and the planets to visually fit and see the model on the screen. The star's mass and delta T were given to us with the initial instructions. I also added big G, the universal gravitational constant, to the project. The data for the project was given to us in the form of a file where the X and Y component of the star's location were located and were used to make numerous calculations for the lab. The first while IDX loop reads the delta X and the delta Y from the file and creates an index to store the calculations in. Because this step compares the final minus the initial position and did it over and over again until the loop was finished, it determines the calculus needed for the next while loop. Computer programs read from the top to the bottom, so I was careful to build the program in order, defining variables before they were used in the calculations. I entered the initial momentum using the star's mass times the V final and the V initial calculations. The delta V and delta P were calculated using the difference between the V final and V initial and the P final and P initial. Because the previous step included the star's mass, I did not include it again in this step. The dp dt variable compared the delta P to the delta T. After calculating dp dt, I used it as FNet. Next, I calculated dp divided by dp parallel. This step solved for the hat of momentum, p hat, by creating a relationship that existed between p initial and the magnitude of p initial. This step was necessary to show the direction of motion. The derivative of the magnitude of p versus the derivative of time was calculated by comparing the magnitude of p final minus p initial divided by delta t. Because the magnitude of dp dt parallel is FNet parallel, it was used to create FNet parallel. And to calculate dp dt perpendicular, you just subtract the parallel dp dt from the total force dp dt. And like the parallel step, the magnitude of FNet perpendicular is equal to the derivative of dp dt perpendicular. To calculate the mass of the black hole, you need to know that the gravitational force depends on the square of the separation between the objects. For every distance, there is a resulting force between the objects. For example, when the star is at position 1, it feels net force 1. When it's at position 2, it feels net force 2, and etc. I utilized the star's distance calculation that compared the star's position minus the origin and called that the star's radius. I used the radius to create the magnitude of the radius and calculated the mass of the black hole utilizing the formula m2 equals magnitude of force times the star of the radius squared divided by big G times the mass of the star. Arrow scale to 1 power of minus 15 and added the m2 to the printout. As you can see, the yellow arrow represents the net force on the star. The blue arrow represents the components of net force perpendicular to the motion of the star, and the third black arrow represents the components of the force parallel to the motion of the star. By observing the length and direction of the arrows as the star orbits the black hole, you can see the forces acting upon the star that cause the star to speed up and slow down.
What is the meaning of the force vector, Fnet perpendicular, Fnet parallel, and Fnet, and how are they different? Force is a single vector quantity that quantifies the interactions between objects. Fnet parallel shows the rate of decrease just before an object turns about a kissing circle and the rate of increase as it leaves. This indicates the rate of change of momentum. Fnet perpendicular is the force that points towards the center of the kissing circle. This is also the force that is perpendicular to the momentum and shows the relationship between smaller radius, kissing circles, and bigger force and larger radius, kissing circles, and increased momentum. Fnet is the sum of all vector forces acting upon a system. What if a new black hole replaced an existing black hole in the same location and the observed star remained unchanged and was affected only by the gravitational forces of the new black hole? Could you tell the difference? No. If the new black hole was placed at the origin, the star's orbit didn't change. All forces must be the same. But our black hole calculator could easily check the black hole's mass.